It's my great pleasure to introduce Brian Cabral, Director of Engineering at Facebook, specializing in computational photography, computer vision, and computer graphics. He started his career, he had a master's degree in computer science from UC Davis, and started his research career actually at Lawrence Livermore National Laboratory. And then before joining Facebook, he was VP of Engineering at Lytro and VP of Engineering at NVIDIA. Brian's published a number of diverse papers in the area of computer graphics and imaging, including pioneering the line integral convolution algorithm. He's a holder of many patents, and he leads the Surround 360 VR camera team. Today, I'm very happy that he's going to be able to tell us about the experience of designing that camera. Thank you, Brian.
Thank you, Joyce. And I'd like to start by thanking the committee and the organizers of this conference asking me to speak. It's really an awesome privilege and honor. I want to start by kind of talking about why Facebook would be doing this at all. Why would we be building a camera? Why are we interested in this? And it's really about our mission. Facebook is a mission-driven company. As Mark Zuckerberg likes to say, and in fact he posted today, that we make money in order to connect people and do the next thing. We don't do the next thing to make money. The next thing is about connecting people and bringing them closer together. And it's not going to be done necessarily on your cell phone on the web in 5 to 10 years. It's going to be with a full immersive presence, or at least that's what we believe. And so we started to think about what that would take. We purchased Oculus to bring that immersion close to you. And as we started to do that, we started to ask ourselves, well, how are we going to get content? How are we going to produce stuff? How are we going to share in that space? It means capturing in real spaces, in 3D, and bringing people closer together. And when we started talking about this, I said, cool, I get to work on hardware, I get to build cameras, it would be an awesome endeavor. But there was an interesting process right in the middle of this about a year ago. I had gone home to visit my folks, and they always ask, what are you up to? So I brought a Gear VR, and I was going to show them some test work we had been working on. And my dad is not technical. Not only is he not technical, in all the 30-plus years of me working in high tech, he's never even come to visit where I work. Not that he doesn't care. He mainly cares that I still have a job and I'm getting a paycheck and I don't have to call him up for money. So he just asks, how is it going, mainly to make sure that I haven't kind of gone off the rails. So I brought a headset with me, and it was a picture of my colleagues. You can kind of see it in the background. It's a picture of one of our buildings down the street in Menlo Park. It's the new big building, so it's a massive space. It's 9.5 acres of an open room. And so my dad's standing in this room, virtually, looking around, and a couple of my colleagues are in the room, and he starts asking, oh, is the one over there with the green hair, does she work with you? I go, yes. How about all those people in the back? He says, some of them work with me, some of them work on other projects. And this went on for a good 5 or 10 minutes, where he was just asking about the place I was working in. And it struck me, it hit me like a ton of bricks, that this stuff matters. He was actually connecting with who I am and where I worked in a way that he had never done in the 35 years that I have been in the workforce. And at that moment, I realized I was working on something way, way more important than some cool technology. I was here to change people's lives, and if I could change my dad's life, I could change everybody's life. Now, if you put this in a broad historical context, we've been trying to do this for a very, very long time. And this graph is not about bits per second in terms of bandwidth. It's about how long it takes to create and share content, to share an idea. And people have been doing this for a very long time. And Up until the electronic age, which starts right at the end of this graph, it was pretty laborious. Started with chiseling and then pressing, baking, writing. It was incredibly slow. Although we made some pretty good progress, a couple of orders of magnitude, but it was basically moving molecules around. And when I started this graph, I thought it was going to be a simple log graph, but it turned out to be two log graphs. One for the mechanical modes of communication, which you see mainly on this graph, out clear through the presses, and then into the electronic age, and that's a second log graph. And it's log in both directions in time and space in a sense, because things are getting faster. And this is important because all of this intimacy and immediacy with sharing content is only possible with our ability to manage and share information. And kind of the ultimate form of information is what we see right now. You come to places like this to be there with people, to see them in 3D, to be present with them. It's an expensive way of doing it. We spent millions of dollars getting here probably, and lots of fuel. I would argue it's not even sustainable to do this forever. So in some sense, the stuff that we're working on, all of us in this room, and this camera I'm about to talk about, is part of a long, long history of trying to get closer together and more immersed in each other's experience so that we can share who we are and what we're doing in a more effective way. And I chose very interesting points on this, having to do with not so much technical milestones as much as communicative and sharing and experience milestone. The difference, I do remember the difference between black and white and color TV and what that meant in terms of an experience. Similarly, when I could record all the music in a library on a stack of small discs with CD players. And as we've moved closer and closer to the right, we've been able to express and share more and more. And now we're at a point where we can share 360 and 360 3D over the wire. But it takes a lot to put a camera like this together. And I would argue that it is not possible to do this without a lot of technology coming together and having come together fairly recently. Each of these elements in technology have been gestating, if you will, separately in a large part over the last 20 to 50 years, depending on the discipline. The first is computer vision. It is now possible to use a lot of sophisticated computer vision algorithms basically off the shelf. 5 to 10 years ago, that was impossible. You would have had to roll your own. And these algorithms, as many of you know, are pretty complicated. And if you have to do everything from scratch, you basically can't build a system like this. All of you here are certainly astutely aware of the advances in CMOS sensors and the ramifications therein. But the ability to have high-quality sensors, a lot of them, and all of them behaving mostly the same way, is a pretty big deal. Again, you can't build a camera like this without this being widely available, relatively easy to use, relatively stable. A camera like this also requires understanding and manipulating color, and manipulating it in somewhat of a new way, but without years and years and years of color science, it would be really hard. A subtle point, which is obvious just upon thinking about it a little bit, each of these cameras has to see color exactly the same way. And as all of you know who have done this, is that most cameras do not see color the same way. Yet, if you're going to put this in a headset and you look around, you don't want one part being blue and the other part being yellow just because you didn't get the color right. It's all of the work that people have done, like Joyce, in color science to make it possible so that these cameras come out looking even, and us knowing what that means to look even. Similarly, you have to know exactly where all these pixels go in ray space. You have to backwards trace or forward trace, depending on how you think about it, out into the scene. You have to know where that pixel lands out in the real world. This means you have to understand how to measure and calibrate cameras. This is well honed in the world of photogrammetry, the idea of bundle adjustment, etc. Well developed, something we could just go and grab off the shelf and use. Again, if we had to develop that from scratch, I'd still be in the, hacking code in the lab. Optics, again, there's a desire to have a particular flavor of optics here. We can turn optics around a lot quicker than we could 10 years ago due to automation and with CAD tools, our understanding of how we can stretch optics in terms of wide field of view lenses, getting the types of lenses that you want, and asking for variants and getting them back from manufacturers measured in weeks and not years. 15 or even 10 years ago, that would have been a stretch. And last but not least is certainly computer graphics. This camera is a computational camera. It synthesizes camera views in order to get the final image. A lot of the math and thinking behind that actually came from computer graphics. The idea of a light field, which this is a variant on, is in fact a lot of that work, pioneering work, was done in computer graphics. So bringing all of these things together allowed us to put this camera together in less than a year, from inception to rolling it out and shooting with it and sharing the results and the design. And it would just not have been possible without a lot of hard work by many people in this room, your teachers, your colleagues. So first of all, thank you, because we could never have done this without you. So you should pat yourself on the back. This is about you as much as about us putting it together. So when we started thinking about cameras, we could have built a lot of different types of cameras. And the first thing we wanted to do is say, what problems are being solved and which ones aren't being solved right now, or are too hard or too expensive to solve. So we fully felt that we had to set the bar in terms of quality as high as we possibly could in order to inspire the industry, show what is possible. It's, in some sense, easier to come down in price than go up. That sounds weird. But if the quality isn't there, it's not believable. If it's not believable, then people won't work hard to drive the price down. And this has been true a lot in imaging, a lot more than you might think. I go harken back to my days at Silicon Graphics. Those machines were expensive. They were more expensive than this thing that we built, yet it showed people what was possible. It drove the industry. It allowed people to say, what if I made a cheaper version? What if I could get it into a PC? So I feel in a lot of ways we are, with these sorts of cameras, where we were in computer graphics in the early 90s. It has that same palpable feel to me. Devices are expensive still, but we can see how to make them cheaper. We wanted the experience to be 3D and 360. As I'll describe in a minute, monoscopic is relatively easy. 3D and stereoscopic is hard, or a lot harder, at least computational. We wanted the camera to be durable and reliable. Now that seems like a duh moment, like why would you make an unreliable camera? But in fact, a lot of people were trying this, and they were, no offense to my GoPro friends, strapping GoPros and everything else together, and it's hard to make those reliable. Let me just to give it some math behind that, a probability of a system like this failing is the probability of any given camera failing raised to the number of cameras, assuming they're jointly independent. And so if you have 17 or 20 cameras, the failure rate's going to be pretty high if the cameras are flaky in any way. So they have to be super reliable. So they have to, in some sense, each individual camera has to be more reliable than your average camera in order to make the whole camera as reliable as an average camera, if that made any sense. Like I said, we wanted it to be fully spherical. We felt that in order to be fully immersed, you would need to be surrounded by information. That if there was a gap in the information, a hole at the top or bottom, or seams, it just wouldn't feel real or immersive. We also wanted to build an open and accessible system. And what we mean by open is literally open source, like you could get a design and run with this. Because we realized very early on that this was a beginning of a journey and not the end, that we didn't have all the answers. We don't have all the answers. There's a lot of smart people out there, and that together we could do something greater than ourselves. So making it open was important. What we mean by accessible was that you could get inside of it. To use an older term, you'd like to be able to open up the hood and get in there and replace the carburetor. It would be nice, because that's how you learn, that's how you make it better, that's how you change it. Now, there's some cost implications in that, because the way you drive costs down is tighter integration, and tighter integration runs against accessibility. It's harder to open up your cell phone and make a repair. Very few of you have done that. Probably a couple of you have, but most of us do not crack our cell phones open and fix them when one of the, leads or transistors go. You hand it in, right? That is not exactly an accessible system. We wanted it to be an end-to-end system, meaning, here again, may sound obvious and dumb, but you'd like to be able to press a button and get a video out the other end. And that's harder than it might sound, and we'll tell you why. But we wanted it to have photons come in and a video come out the back end, a stereo video come back in. So that was the goal, the goals we set out for ourselves. And we set out to do them in the normal Facebook way, which was as fast as we possibly could. And the reason we wanted to do that was, again, because we didn't think we had the answer. It was important to get this out to all of you so that we could rev it really fast, we meaning all of us. So this is review for most of you, but it's an important intro to the next part. So we felt monoscopic 360 was pretty much done. You can do this with 1 or 2 cameras. 2 is the most common. You get them with very wide fisheye lenses, make sure they overlap a little bit, and figure out how to deal with the overlap and feathering, which strictly speaking is as hard as the stereo problem, but you can fake it enough so that you can produce reasonable images. And that problem we felt when we started this effort was going to be solved by a lot of commercial products at various price points, and sure enough, you can go on Amazon and buy cameras like this. We think that's awesome, that's important, it's an entry into this space. But it's only monoscopic, and it means that if you look up and around, it's as if you're inside of a spherical Sistine Chapel, right? Everything's painted and far away. It looks cool, but you can tell it's flat. It's two-dimensional. So in order to do 3D 360 is you have to have a lot of stereo overlap, which means you have to have a lot more cameras. And things start to get difficult very quickly. First of all, you have to decide how much overlap. You have to decide how many times you see each point in the scene. And this affects the design space of the camera. And I'm going to walk you through a whole bunch of variants we thought about. Now, the answer we came up with is not the answer. It's an answer. We chose that answer for a variety of reasons. But the important aspect of this is this design space is kind of hard to think about. I'll get into why in a minute. And it's complicated. So there's a lot of design points that are interesting, and we've been encouraging people to try different points in the design space, and they have. The other, of course, is the sensors to use, and probably nowhere more than this effort was the issue of rolling versus global shutter. Because not only is it in the wrong position in the image if you have a rolling shutter, and all of you kind of know the difference between this. Most audiences, I have to explain this, but here I'm sure everybody knows what this means. But I think the really important thing about this is it's wrong in 3D if you have a rolling shutter. So just think about somebody's face moving real fast. The top of the nose and the bottom of the nose are in 2 different spots. And in the end, you're trying to fuse and reconstruct that. So if you can't reconstruct that easily, it's not a mere matter of shearing images to fix the rolling shutter. You actually lost 3D information that you want to recover. So global shutter is pretty important. It's not like you can't attack this problem with a rolling shutter, but it's harder. And as you'll see later, the hardest part of this problem is in the software. And anything we can do to make that easier, we did. And that's one of the reasons we chose global shutter. The other is that you have a whole bunch of design space parameters that you don't have in a regular camera. And you have to constantly reevaluate these depending on the availability of technology and cost. The first and most important number I think about when I look at a camera like this, and the first thing I try to figure out when somebody says, oh, I have a new 3D or 360 camera, is pixels per degree. That gives you sort of an estimate of, at least optically and with respect to the sensor, what's its resolving power, at least to first order. And this is the main number that you play with, because if you want more pixels per degree, you either increase sensor resolution or you decrease the optical field of view. And if you decrease the optical field of view, your overlap changes. And if your overlap changes, you now have to add more cameras in order to get more overlap. And all of that wraps together to give you how much angular and depth resolution you have. And these things all fight with one another. As I mentioned earlier, you want to reduce the camera count because of cost and reliability. But if you increase the camera cost, you can use more off-the-shelf optics, and you get more angular depth. So these things are absolutely in constant tension. So every time you go out to design a camera, you go, where do I want to be in the price point? What do I want? Where do I want to live in this arrangement of configurations? And so designing cameras in this space is exquisitely difficult, because you've got to make all of these decisions, and once you've locked them down, you're rocking and rolling. You're going to go down that path. So it's pretty tricky. So just let's look at some. So one, you can do small cameras, so you can get them packed together tightly, but then you need fairly wide field of view lenses. That means that you either have to use really high resolution sensors, or you give up and say, I'm going to have kind of a poor resolution camera. You can then try it with larger cameras, bigger sensors, but now your physical size is not as small, it's a little bit bigger. You're still using fisheyes, but they could be expensive. So an example on the extreme edge of this is like REDs. You could go out and buy 6 RED cameras, do this, get fisheye, wonderful image quality. It'd be pretty heavy, it'd be very expensive. You could go completely in the other direction and say, heck with it, I'm going to buy a bunch of cell phone modules, tie them all together. Then you have the reliability problem. Remember, you have to synchronize all of these. Keep in mind, it's not enough to have a global shutter. You have to have all of them fire at the same time, so they all have to be wired up and synchronized. You could use wide-angle lenses, but you can only pack them so tight, too, depending on the size. So there's another trade-off there. We went kind of in the middle of all of this. So we tried to pick a spot that was sort of in the middle. And it's by no means the right answer. I can give you 10 more reasons why I would do it differently again and again, and every time I implemented. We chose 14 smallish cameras, but they were highly reliable. We used industrial cameras, as you'll see, for reliability reasons. But that is just one design point. And if there's any message to come out of this, is experiment. Try different things. Decide what problem you're solving and at what price point, and that will dictate which configurations. So in such a configuration, you are kind of limited by the physical module size, and that's also a dictate. Another aspect of this is as you well know, it's one thing to do all of these paper studies, write simulators, et cetera, and we've done that, and that is important. That's super important. But equally important is just to build stuff. So while we were simulating and designing our software, we were trying all sorts of things. Some of them crazy, as you'll see. All of these we literally have built at one point or another, mainly to me proving to people that this wouldn't work. But all kidding aside, the ability to rapidly prototype and try things out and see where they fail is pretty important when you're designing, entering a new technology. The one nice thing about Facebook is they actually encourage this behavior. They don't care that you're doing a couple of wacky things or maybe a dozen wacky things on the way. Try it, experiment, toss it away, do it again, rinse and repeat. And that gives you a lot of confidence when you get to a solution that it's going to work. And we did this literally on a weekly basis. We just kept churning out variants. And this is sort of where we landed. And I want to take you inside of this camera. I talked about accessibility. This is very accessible. It's about this big. You can open it up. You can wire it. You can put an oscilloscope on the wires and see if something's not triggering. They're all off-the-shelf cameras. You can replace them easily. So all of this made it so that we could test and implement very rapidly and make it accessible, and also make it buildable by others. So let's take a peek inside. This is actually the CAD drawing we used. We made a film of it. It has 17 cameras, which I'll talk about in a minute. Each of them are global shutter 4 megapixel cameras. Their output is USB 3, which is a challenge. We have 17 cameras here, so you have 17 USBs running at 30 hertz. That's around 15 gigabits per second. We actually record RAW. The reason we record RAW is we have to have fairly high image quality on the way into the stitching code, which I'll talk about before. We're really sensitive to sub-pixel behavior of the cameras. We used 2 different types of lens, so it's heterogeneous. We used a fisheye on the top and wide angle on the side. We did that in order to make a trade-off against resolution horizontally versus looking up. The reason we could get away with that is more on the display side than the capture side. The current display technology and all the stereo images you see in Oculus and Rift and like devices are actually omni-stereo images. It's a technique developed by Peleg in the late 90s, and the basic idea is that for each eye you have a thin, infinitely thin or 1 pixel thin image that's in stereo that's correct for the direction you're looking at, but wrong everywhere else. But as your head turns, you're always perfectly in stereo for each eye. And that works amazingly well. The problem with it is if you take that strip and keep it stereo clear up into the top, the stereo's flipped. And I'll let you think about that. But if you have 2 stereo images and they meet at the top and they're just left, right eye stereo, they'll be wrong at the top. And so the cheat everybody does is they fade to monoscopic at the top and bottom. And that keeps you from looking up and going, what the heck's going on up there? We exploited that by putting a fisheye on the top and just having 1 camera up there, and that's why we get away with it. But it is a hack. So we exploited a hack on the output, on the input. And that was another interesting thing. We wanted not to overbuild relative to the output device, which we could have easily have wound up doing. So we were conscious of both the pixels per degree on the output device, but also the display limitations. Okay, one more. Yeah. So we put a cover mainly for beauty, but also for protecting the lens. Mainly, we run this camera with the covers off because the top is cheese-plated, so you can grip it onto almost any configuration. The top and bottom plates are rolled, milled aluminum. We give these CAD drawings away on our website. You can build this yourself, and you can look at exactly what we've done. The plates serve 2 purposes. One is just rigidity, make it rigid. And that rigidity is important when you're going out and shooting and handling the cameras. It also acts as a heat sink, which is important. Heat is probably the biggest problem with these cameras. And as you try to integrate them more and more and get them closer and closer together and put more and more logic on board, the worse and worse it gets. So heat is a huge design point. We used a blunt instrument here and just made it two big plates, and that solved the problem. We've never had any heat problems, but we overdid it probably. And then everything's screwed together with standard components. So everything's standard except this milled plate, which we tell you how to build. And back together. So as I mentioned, there's a lot of bandwidth required. Like I said, we gen lock all the cameras, so they're lock sync, they're global shutter, and you have to put that data somewhere. And that's another tricky thing, is getting enough bandwidth on your output I/O. We use rated SSDs to pull that off. And it's handling that much data is challenging, and then processing it equally so. So we wanted this to be buildable by other people, and so we actually asked one of our art designers, so he's not an engineer, we gave him all the parts, we gave him the instruction manual. We have an IKEA-like instruction manual, which is kind of cool. And we told him, here it is, go to it, and we filmed him doing this. It took him about 3.5 hours. This is time compressed. A couple of things. He built it himself without us helping him. It did work at the end. So he built a working camera. We can build it in about an hour, somebody who's done it a lot, but it takes about 3.5 to 4 hours if you have all the parts laid out. We tell you the parts, the part numbers, the tools to use to reconstruct this completely. It's pretty exciting. He was quite tired at the end of this. He was kind of sweating because we had lit it, as you could see, for the filming. So it's pretty neat. It was fun to. I wasn't there for the filming. I just saw this afterwards. I was sort of amazed. There he goes. Oh, seeing him wipe the system off like that. One of the things that's interesting is you have to keep these lenses really clean. And that is because of the next problem, which I'll get to. Because the hardware is the easy part. Stitching all of these images is hard. And I'll walk a little bit through this math, but it's mainly there to tell you kind of how hard the problem is. How we actually reconstruct this image is using something called optical flow, which many of you are familiar with. But basically what you're trying to do is create a synthetic camera between any two of the existing cameras. Because you're creating one of these slits. You need this virtual slit camera, one for the left eye and one for the right eye, and you have to fuse them. And so what you have to do is say, what does one pixel in one image look like, and how do I find the vector field? So this produces a vector field that says take a pixel from here and a pixel from here and flow it into this new pixel. There's a data term, basically says, do these pixels match and do the gradients match? They also have to not flicker in time. So if you just do it for one frame and not the other, a little bit of noise, a little bit of change in position will cause the flow solver minimizer to possibly come to a different minimum, and you'll see it as flicker, which is really annoying in a headset. So we temporarily regularize or smooth. We also do a type of spatial smoothing with, I think it's an L1 norm. On top of that, you'd like to make sure that if you've moved your vector field and your coordinates, in this case u of x and y and v of x and y, you may get a little bit of residual spatial noise, and we get rid of that with a median filter. And then you'd like the flow as you evolve the equation, because you kind of evolve it over time, you'd like it to diffuse almost, kind of in a continuous fashion. You don't want to make a big jump every time you do a computation, and that's what the flow diffuser does. But this was a hard-won equation, meaning we kept working at this to make it fast and make it work consistently and well, because we have to process a lot of data. We can do about a minute or two overnight is about what we get. So it's still pretty painful. There's lots of room for work here. So if anybody has a graduate student that's bored, lots of papers here. So what does this look like? How do we actually do this? We take the images, this is the image out of the camera after it's been run through the ISP, and we warp it to spherical coordinates, or so-called rectify it. Then we lay them down side by side. And you might say, we're done, it's awesome. Stop. Let's go back. Okay. But if you look closely, you can see the seams, because now just lining them up that way means that you have parallax and depth errors, and that's what you're seeing there. And so this is where the optical flow starts to come in. So now this is optically flowing two images to create an intermediate image that you see there. We show you the depth image in two different, or depth estimation relative to the flow, so you can back out the depth from flow, at least approximately. This is the flow vector of where these pixels would get moved to, and this is the thing on the right is the final result. And hold it, stop, back. This thing is, come on, I want you to, there, damn it. You see it move, but this animation is not, see there, it touched like, you gotta love Keynote every once in a while, it does weird things like that. Okay, don't move. I will walk, okay, stop. So this is it stitched horizontally and fixed, and this is the left eye and right eye, and if you think real hard you can see it that it is and has stereo parallax clear across. But I said we had these top cameras, God, back, top cameras, and what we did was flowed from the top to the bottom, and we actually have stereo overlap in the annulus, and that annulus on the bottom is the overlap between this picture on the right and the top picture. You get this annulus. And that is the warped image after you flowed it to match the sides, and there it is reattached to the, no, back. I know why that, don't move. Okay, it's being mean to me. Anyway, I'll do it one more time. It'll attach the top and it's consistent. So we used flow in two directions. We use it side to side and top. So this isn't interesting unless you go and actually do something with the camera, i.e. shoot with it. So bravely, a little over a year ago, or a little less than a year ago, we decided to do a shoot, and we wanted to do a people shoot. We wanted to shoot people. And so somebody in our creative team had a bright idea of saying, oh, we'll shoot in a train station and show multiple different pieces of action, of families leaving and meeting and greeting. They didn't tell me that the station that they wanted to use was Grand Central Station. Now, shooting in Grand Central Station presented all sorts of nightmares and problems, not the least of which is you have to do it at 2 o'clock in the morning when there's nobody there. So all the people you see here are actors, number one. Number two, at night, even with all the lights on, Grand Central Station is about 40 lux. And I know because I've walked around with a light meter a lot in Grand Central Station. So it is dark, relatively speaking. It's not a well-lit environment. We actually brought in 8 helium ballooned lights, and each one of these lights would fill a small chunk of this room. They were huge. You can see them in the reflection in the mirror if you look closely. So this is the shot. This is it after it's been stitched. This is one of the monostopic images. You can download this from our web. You can also see some of our mistakes in there. You'll see some flow errors that we made. But this was shot continuously for 3.5 minutes, so it's a continuous take. You're only seeing a piece of it. I'll play it again here for you. It was super exciting to shoot this, and for a number of reasons. The ending of this film, we actually put the camera on a boom and raised it into the center of Grand Central Station, which is a pretty epic experience. I don't think anyone's ever had a shot from there ever. So yeah, it was pretty fun. The other thing that caught me off guard was the lights in Grand Central Station are very orange. They're probably close to less than 3,000 Kelvin. They're orange. They're like almost sunset lights. And so when the lighting director, who was fabulous, asked me what type of lighting, I said, well, try to get halogen, get something warm, because these lights are warm and we want to color match the lights. He did an awesome job, spent buku dollars bringing these lights in. Great. So we get back to post-production, and the color matching, and the director says, no, I want the scene to be a little edgy and cool. Now it turns out that we used a sensor whose blue channel was the weakest part of the sensor. So it's the noisiest, and he wants it blue. And I tried to talk him out of it. There was no talking him out of it. He says, you don't understand. I said, yeah, I do, but he kind of won. So color matching this was exciting. As you can see, this is pretty neutral, pretty cool. And go and look up on the web Grand Central images. If you've been in Grand Central Station, you know it's really a warm scene. So we had this like extra challenge in post-production. And I mentioned color earlier, but getting color calibration, and in fact, you would like desirably to hold your color linearly clear through the pipeline to the very end and let the color matchers at the end do their job in whatever tasteful way they want. And that means preserving lots of bits throughout the pipeline, ideally. And that is kind of an odd thing because most people, when they shoot video, don't preserve those bits. Here you should, and you're also super sensitive, as I mentioned, that you want this nice and even across the entire scene. You don't want one part of the scene to be orange and another part to be blue. Try color matching that at the end. It's almost impossible, almost impossible. So it was a pretty heroic effort. And so, welcome. So all of this is available on GitHub. You can download it. You can look at all the code, the calibration code that we include, the control software for the camera, and all the stitching code is there, freely available. You can peruse it, you can compile it, and you can fix all our bugs for us. So this about wraps it up. Thank you for your time, and I think, do we have time for questions?
I believe so.
Okay, great. Let's ask some questions.
If you compute the total visual resolution of a sphere enclosing your head, it's around 600 megapixels, and I wonder, can you do a rough count and tell us how close you are to that?
Yeah, we can output around 8K by 4K per eye with this camera. And that is resolution matched to the output device. We were aiming kind of for a Gear VR and Rift. So are we there yet? No, but I wasn't going to add any more pixels than I had to.
How do you control exposure for all the cameras?
We have a user interface, and it's a global exposure. We have found that you don't really want to let it free run in auto exposure, even if you do a global auto exposure, because in a headset, if you're having fluctuations in exposure, that's quite annoying. What most people who shoot like to do is have a live preview and have a histogram, and then make sure that it's reasonable. The other reason you want to do that is, and it's a great segue into an important point, is that you have a dynamic range problem with cameras like this. The illuminate is always in the scene. Something bright is always in the scene if it's well illuminated, and a dark corner is almost always in the scene. So you're going to have to make an aesthetic judgment given the dynamic range of the sensor to where you want to put that dynamic range, and that's usually, we currently do it by hand and interactively with the user interface before the shoot. Almost all 360 cameras do that.
Yeah, you didn't say too much about the system that is used to capture this. Could you discuss a little bit about that?
Yeah, so it's pretty brute force. It's a ruggedized, high-performance computer with enough PCIe slots to suck all this data out and send it into a RAID disk. It's about that big with a self-contained monitor. Probably, I would argue, the weakest link in this system is just hauling those cables around, making them consistent and working well. The camera itself has never failed in the field, but getting the cabling wrong and other human errors and related errors are an issue. Yes.
So as far as the depth goes, how close to the cameras can you get and how far can you get?
Yes, great question. We can get comfortably around 8 feet before the flow algorithm starts to break down. We think if we worked harder at it, we could get down to like 5 feet. That is a real trade-off between the field of view and overlap and the baseline of the cameras too. The smaller you make the baseline, the better off you are. And we made it fairly large, which means our sweet spot goes out to 20 or 30 meters. So, you trade that off for sure.
Have you tried taking video of a scene where you have more than one color, temperature, light source?
Yes. Okay, this may shock you. Color temperature, as long as the cameras are consistent, is not a big deal on headsets. And that is, I believe, and I'm waiting for one of the fine color scientists here to either prove me right or wrong. I have a conjecture. It doesn't matter because you're in a headset and you're immersed. The warmth matters, but if one part of the scene is warm and one part of the scene is cool, and your brain totally takes care of it. At least I haven't seen a problem with that.
How many times did you have to shoot that scene to get that 3 minutes video?
We shot it over 2 or 3 nights. The choreographing was what was hard. We wound up with 20 good takes. 3 we liked, and we narrowed it down. So if you include the practices that people did the week before, because everything was choreographed, it's weeks and weeks. But the number of takes was a typical Hollywood shoot, maybe a little longer because we had more choreographing. But we didn't have to reshoot because of camera failure. We had to reshoot for artistic purposes.
So technically it worked on all 20?
Yeah, it was amazing. God knows I was nervous through the whole thing, but it worked well.
Hi, thank you for your very interesting talk. This is certainly very technically interesting to this audience. But back to your first example using your father, why would something like this be interesting to the regular user, and how will it change my life?
You're asking me to predict the future. Let me give you another example. Wouldn't it be great if your grandparents who live on the other side of the world could visit you and your kids anytime they wanted and really sit and play with them on the ground or interact with them and be right there with them, see them in 3D, be present with them and interact with them. It's why we share photos. It's why we keep memories. It's impactful now. I think it'll be even more impactful later. And that's why I think it matters. We're not there yet. We're just beginning. This is a beginning of a long journey. So I think that's why it's valuable, because people value memories and experiences. They want to be places they can't go. And we can deliver, hopefully help them connect and deliver that richness and value in life.
Well, thank you very much. That was really great. And I would like to thank Brian again.
Thank you.